Uh, and one thing to note about the one-to-one model is that this doesn't really change with the number of processors you have, because at the end of the day, if you have a single processor, if you have multiple, or if you have multiple processors, it doesn't matter, right? I mean, it's a one-to-one. And this is why I have always been talking about kernel threads as, I mean, there isn't really a difference between user threading and kernel threading, okay? And that is the Linux model, and this is how most Windows operating systems work right now. Now there's the many-to-many threading model, where you have basically, where you have many user threads mapped to many kernel threads. And it can be basically, the number of kernel threads can be smaller or equal, which just makes it more fun, the number of kernel threads. So you have 50 user level threads that gets mapped to 5 kernel level threads, for example. And then there are 10 user level threads per kernel thread. But then if out of these 50, 45 user level threads exit, then you just have 5 user level threads remaining and 5 kernel level threads in action. Once you have one of these 5 user level threads starting to exit also, then you have one extra kernel level thread that is not used, and in that case you start basically removing some of the kernel level threads. And this was designed for mostly multiprocessor machines, and it was used for it was at least tried during some times on Windows, and it was actually the way that it was used with ancient Solaris versions. That's basically before Solaris 9. I'm not sure what Solaris version they have right now, but that is roughly, I think Solaris 9 is something like 2006, 2007 maybe. Even, I can't remember the exact date. Okay, so now you have, and this is the many-to-many user level thread model basically. Okay, and there are plot twists to all of these 3 models. There is one where you have a per processor kernel thread with multiplexed green threads, so a many-to-many threading model, but you have for each processor one single kernel thread. So if you have a multi-core processor with 4 cores, then you'll have 4 kernel level threads, but then you have green threads that get multiplexed on that. Okay, this is one plot twist. The other one is basically what is called scheduler activations. It was actually suggested in 1993. It got some implementation, some momentum back then. The paper that was published that basically described that model got something like 600 citations. This is pretty large number for computing science papers in general. And there basically the plot twist is that you have explicit support for user level threading. So it's no longer that you have green threads, and it's no longer that you have user threads, and it's no longer that you have kernel threads, but you have both kernel threads and user level threads, but the kernel is aware of the user level threads. So that's another plot twist. And for the user level threads, there is a user level thread scheduler that basically talks to the kernel thread scheduler, and that basically schedules the user level threads. That tells basically the user level threads the user level scheduler tells the kernel level scheduler that now this is the user level thread that you should be running. And once the operating system, the kernel level scheduler, decides that it needs to evict one of the user level threads, it will get in touch with the user level scheduler asking for another user level thread. So it's quite complicated, and it's called scheduler activations. And then the who implements the user level thread? That's not the user. Okay, so that's not you and me when you're programming, but someone else. And that someone else, just to add to the plot twist, is either the operating system. So you have explicit support in your operating system for doing that. And that was actually the way that some Windows versions implemented that. Or through a threading library, which is something that is different. There is something that is called a threading library. Well, it basically controls the way that the applications does threading, or Martians basically. I mean, someone from Marsh implements this user level threading scheduler for you. And this is an example of one of the threading libraries that were implemented to basically do user level use scheduler activation. So this is a direct link that you can basically go and check that. And of course, this is almost obsolete. Then so this is basically how screwed the threading model space is. And I think that the most elegant one, the easiest one to understand, is the one-to-one model, which has been almost the Linux supported version. Actually, scheduler activation, some people tried implementing them in the Linux scheduler, but it never got traction, for example. I mean, I think it was suggested it might have even be integrated as optional way to do threading, but it never actually got traction. And we are back to the one-to-one model. We have always been on the one-to-one model actually with Linux. So it's very elegant, very clean. It does not really make life very hard to understand from a programmer's point of view, right? You have one user level thread versus one kernel level thread. Voila, it's over. So enough with this. So let's talk about how we kill the threads. And there is actually a file that's called in kernel, in the kernel folder, that's called /exit.c. And there you have a do exit function that basically gets the thread. That exits the thread that is running. That basically moves the thread from the runnable state to the finished state, basically. Okay, and that's the way you basically kill the threads, using the do exit threads. And we have actually discussed that in some cases if you kill a thread, the children do not get killed. And in theory, in most operating systems books, they will tell you, yes, they get killed. I have actually given you examples of cases when you can find that they do not get killed. But actually in Linux, there is even a function that's called find new reaper. And that is basically a function that tries to reparent all the children. So if a thread dies, it might call, I'm not saying it has to call, but it might call find new reaper. And that is basically a way for the thread's children to be reallocated to another parent. And that parent can be init. So you can have basically threads that were running in, for example, your database, and then you kill your database, but these threads have been raped to init. And of course, this is either something that you absolutely want, because you want the threads that were starting by a program to keep running, and that program, if that program dies, you want this to continue running. Or something that you absolutely do not want, because once you want your program to die, you want all children to be cleaned out. And this is design choice basically that you need to do in your program. Okay? And do exit basically takes these steps to exit a thread, to kill a thread. And in the beginning it raises a flag that says that it's exiting. And then it calls a function to remove any timers that are associated with this thread. It calls a function to release the memory structure held by the process, and if no other process is using the address space, then the kernel will destroy that part of memory later. not now, but it just says that I'm exiting, so I'm no longer using this part of memory. And if there are any locks, semaphores that are held by the or semaphores that are held by the process, then they are released. And we are going to talk about locks and semaphores actually very soon, as in the next lecture. And it calls exit files and exit file system to decrement, to basically, if it's open, if it has any files that are open, then it closes all of these files. I mean, it tries to exit them. It basically says that I am no longer use these objects, okay? And as we said that, well, these files can be actually control over hardware, for example, because it's open, the open and close semantic, basically, that we have discussed, okay? It sets the task's exit code, and that is basically if it was successful, for example, if it was failed. I mean, there are multiple task exit codes, so it sets the exit code that would then notify the parent of how this task was exited, basically, of how this thread exited. And then it notifies the parent that it's exiting, okay? And then it actually calls the scheduler to tell the scheduler that, oh, I have just exited. Okay, so these are the steps that are taken by the do exit system call. The do exit kernel method.